Well, if we look at a recording studio, this is the budget version of a recording studio. This is the kind you make when you're just getting started. You buy some egg cartons or some old sweaters, or if you're really rich, you buy some foam. You put it up on the walls, and the reason you do that is because you want the sound to come from the loudspeaker. But that same sound goes out from the loudspeaker towards the walls, and you don't want it to bounce back. That's the goal in a recording studio. So what you want is just the sound from the loudspeaker and no reflections off the side walls. That's the cheap way to do it. If you have some more money, then you hire an architect who knows something about acoustics, and they design a shape like this that looks sort of like a barn in New England, but there's some math behind this. The problem with this space is that although this works really well for what you hear coming out of the speakers, as soon as you get somebody on staff and there's somebody to talk to next to you, this is a very strange space to talk in. It's a very dead room, and it feels like your voice is just getting sucked away all the time. It's like living in a black room. This is a lot more comfortable to work in because it still has reflections. The trick is that these angles are designed to move the reflections from the speakers away from you. So you get the sound from the speaker, but instead of reflecting off a sidewall over here and coming back to you, it gets bounced away from you. So the reflections are still there. They're just being directed away from the listening position. And that's true for both speakers. You still have a room that's very reflective. You're just sending the sound somewhere else. And what that results in is something called a reflection-free zone, where the engineer can work without getting those sidewall reflections. They're only hearing what's coming from the speakers. But they can still work with other people and not feel like their voice is getting sucked out of their face. In a normal living room, this is my house. It's very sparse. I can't afford furniture. What you get are the sound from the loudspeakers, but you also get those sidewall reflections. This is very normal. So what we normally do is tune a loudspeaker to account for those reflections. And we change the timbre, the tone color of the speaker, to compensate for what those reflections do to the sound. But our goal, remember, is to make the experience at the listening position the same as what it was in the recording studio. So the question is, why are sidewall reflections bad in recording studios? Why do we want to get rid of them? We're going to do a test. I want you all to close your eyes. You have to trust me. Close your eyes. Close your eyes. Your eyes aren't closed. I want everybody to point to my voice. You're looking. You're cheating. Where am I? Excellent. Everybody's pointing at me. Now, keep your eyes closed. Tell me if I went further away or closer. Now I'm over here. Further or closer? Further. Good. Everybody wins. How did you know that? Well, you just know, right? Of course you know. What your brain is doing is it's taking the sound that's coming from my voice to you. I'll pick on you. So it comes directly to you. In addition, at the same time, the sound goes from my voice out to the sidewalls and then bounces back to you. And what your brain is doing is comparing those two things. It's comparing the direct sound to the reflections. The louder the reflections get relative to the direct sound, the further away I am. Basically, you hear more room. So as I go further and further away, there's less direct and more room. If I get very, very close, there's more direct and less room. That's not something I'm doing, and it's not something the room's doing. It's a product of the distance between us. That's how you tell how far away things are. But that's also how you tell how far away the speakers are. So what we want to do is make a recording where those reflections, that information is in the recording, and it tells you how far away things are within the recording. But what you don't want is sound coming from the speaker, bouncing to the sidewall and over to you to say everything is this far away. As soon as we have something bouncing off that sidewall from the speaker, it overrides the information in the recording, and you lose distance and depth. Everything starts to collapse, and I'll show you some pictures later to illustrate that. The problem is that with most normal loudspeakers, that happens, and it happens differently at different frequencies. When I stand here and talk to you, the sound goes this way, it also goes this way, and you get both. When a sound comes from a normal loudspeaker, it goes forward, but only the low end goes that way. Only the low frequencies go that way and bounce off the wall. So what you have is something that looks like this. At 300 hertz, you get a very wide beam. And that means sound going towards the wall is quite loud. And you get a lot of energy at 300 hertz off the sidewall. At a higher frequency, it's a very narrow beam. And there's no energy bouncing off the sidewalls. Nothing goes that way, so there's nothing to bounce. It's a bit like you have a light bulb in the low frequencies, but a laser in the high frequencies. And as a result, the low frequencies sound very far away, and the high frequencies sound very close. And at another frequency, it might be different again. This is just 3 frequencies, but when we're being geeks in the cube, which you'll see this afternoon, we need more information than this. We need to know how quiet is it, and we need to know more information at more frequencies. So we look at graphs that look more like this. I'll skip this stuff. We look at something that looks like this, which is a little more complicated, but gives the same information. At 300 hertz, right here, the beam is very wide, the same as you saw a moment ago with the pi. At 2,500 hertz, a higher frequency, about there, it's very narrow, and at a higher frequency, it's wide again. This is a really normal behavior for a loudspeaker. We see this all the time. The problem then is that that means that we're getting a lot of energy off the sidewalls, because there's more energy going that way, at 300 hertz, no energy off the sidewalls at 2,500 hertz, and a little bit at 7,000 hertz. So if you listen to Suzanne Vega singing Tom's Diner, you know, deep, 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 you know that song? Yeah, everybody knows that song. What happens is that the low end of her voice sounds very far away as the speakers. But her S's and T's sound very close. And suddenly she's in 2 places at the same time. It's like somebody stretched her in space. So you have this strange 3D effect that's very unnatural. So this is bad. What we want are 2 things. We want a beam that's narrow, so we want all of these to come closer, and we want them all to be the same at different frequencies, so that we have the same energy at all frequencies going towards the sidewalls. And that way, Suzanne Vega sounds like she's in the same place as herself. I think I said that right. So our goal is to have 300 hertz and 2,500 hertz and 7,000 hertz and all the other frequencies to be the same width. That's our target. We have a narrow beam, and they're all the same. So what that means is that our target looks more like this. This is our target. That's what we want. That's not what we got. We'll get there. But that's what we're aiming for. This is what the geeks call constant directivity. That means this is the same at all frequencies. But essentially it means it's the same beam width at all frequencies. And we want it to be a narrow beam. How do we do that? Well, we have 2 options. One way to do that is to change the shape of the loudspeaker. We can build a loudspeaker that is a specific shape because the width of the beam is defined by how the speaker looks. So we can build a loudspeaker that has a shape that gives you that. The problem is that that really only works for you. You're in the beam and you're not. So you lose. Sorry. So it's not a very friendly loudspeaker. It's great if you have 1 chair and no friends. Thank you. I have 1 chair and no friends. My wife loves me, but that's about it. If you have friends over, say you have friends, then what you want is something that's a much wider beam to be able to share that experience with other people. So if you build a loudspeaker that's shaped to give you this, then you're stuck. You have 1 chair and no friends, and you'll die alone. It's an unhappy life. We decided that wasn't what we wanted to build. So what we did instead was put extra drivers in the loudspeaker, meaning extra tweeters, extra mid-ranges, extra woofers. What those are doing to generate this beam width that we're aiming for, we have a tweeter on top, a mid-range, and a woofer, and we play those as if they were a normal 3-way loudspeaker. And then what we say is, let's look out the side and find out what's going that way. In the low frequencies, if there's too much going that way, we'll use the back woofer to absorb sound. So we'll kill sound going that way and make the beam narrower. But at a high frequency, if it's already too narrow, we'll use the side tweeter to help and send more energy in that direction. So the extra drivers, in essence, are being used to control that beam width. But because we're doing that with extra drivers, that means we can make the beam width whatever we want, and we can change it to whatever we want. This is what BeoLab 90 would look like if we measured it just using the tweeter, the mid-range, and the woofer, and turning off all of the other drivers. So if we just made a normal three-way loudspeaker that looked like that, we'd have a fairly wide beam in the bottom. It would get wider, then narrow, then wide, then narrow. It has a strange shape. So this isn't what we want. What we do then is we make extra signals, 15 of them in fact, because each driver has its own amplifier, its own digital to analog converter, and its own DSP with its own filtering. Everybody is an individual in this speaker. And what we do is we take the other woofers and make this narrower. We take the extra mid-ranges and make this wider, and so on, and result in that. So this is the narrow beam width when all of those drivers are working together to deliver what we want. I'll go back. Pictures are, yeah. So this is what happens if we do nothing, and this is what happens when the narrow beam width is on. But remember, we're doing this actively, meaning we're achieving this by turning on those extra drivers and by changing how they respond using filters connected to each of them. What that means, and I've already said this, is that since we have control of those extra drivers, we can make them whatever we want. So for example, in one mode, we have a narrow beam width, but if I change how those extra drivers behave, I can make a wider beam width. So the person with one chair and no friends has a party, puts in 2 extra chairs. They have an app, they can change to a wide beam width, and they have this, and now the friends are happy. When the friends go home, you throw out the 2 chairs, you go back to narrow beam width, and you're happy by yourself. So what you're doing is using an app or using the B&O TV, or, as you'll see later, programmed to a different source, you decide what beam width you want according to the situation you have. You're not locked to one beam width because of the shape of the speaker. In fact, if you have more friends over, you have a party, what we can do is say, let's just send sound to all the drivers, and that looks something like that. Now you can see here that we run into trouble. This gets a bit messy up here, but remember, it's a party, and so it really doesn't matter. This is what we call Omni Mode. So this is what happens when you're just moving around the house with a lot of people. You're not really paying attention to how things sound. You're not sitting in the sweet spot. Everybody's just enjoying themselves. Okay? So these are the 3 beam widths that we have available in the app. You simply change on a single screen between those 3 beam widths. What's the effect? I'm sitting here. It's all good for the geeks, but so what? If you're sitting right there where you're sitting, since you were the winner, and we play a recording called Bird on a Wire by Jennifer Warnes that was recorded in 1989, you sit and you close your eyes and you focus on how far away things are. Where is she? Where's the backup vocal? Where's the triangle? Where's the bass? You get a map something like this. So you sit here, the BeoLab 90s are here, and her voice, when you're in narrow beam width, will be somewhere between you and the speakers. She'll be out front of the speakers, and she'll be a pinpoint in space, right here for you. Her backup vocals will be somewhere behind. The choir is way back. But what happens when I go to wide mode? Remember, with wide mode, what I'm doing is changing the beam from about plus minus 45 degrees to plus minus 90 degrees. So now there's more energy going towards the sidewall. And what that does is it tells your brain how far away the sound is. So you're getting less information in the recording and more from the room. The result of that is something like this. So what happens is she gets further away, closer to where the speakers are. And the backups get closer. So everything collapses. You lose depth. Depth is the distance from the closest source to the farthest source. So this is reduced. At the same time, those pinpoints become clouds. That's the cost of having friends. Maybe it's worth it, maybe it's not. Depends on your philosophy. This is me, this is most people. So you can choose. You have more similar sound for everybody, and the cost of that is depth in the recording. Or you can drive a motorcycle. It's a great ride for one person, but it's not the same as riding with two people. As I said, we also have this Omni Mode. And what that does is gives you an enormous amount of information about how far away the loudspeakers are. And the end result of that is basically a line of instruments that's as far away as the speakers. So you get this, the band sits here. And they become more cloudy again. Are we okay? Good. Now, as I said, that's done actively. What we can do then is compare how BeoLab 90 compares to both its competition and our own loudspeakers. This is a very well-known audiophile loudspeaker that we put in the cube and measured. What we're doing here is saying, let's measure how the speaker behaves on axis. That's 0 degrees. And whatever that is, let's find out how far you have to rotate around the speaker until you drop by 3 decibels. That's half the power at any frequency. So we take a frequency and we start rotating until we get to 3 dB down, 3 decibels down. So half the power, then 6 dB, 9 dB, and 12 dB. You can see at a low frequency, like 100 hertz, you can never get to a place where it's less than 3 dB down. Sorry, where it's more than 3 dB down. So you can go all the way to the back of the speaker and it's just as loud at 100 hertz as it is at the front. Whereas up here at 1, 2, 3 kilohertz, you only have to go about 45 degrees and you're down by 3 dB. What that means is 100 hertz is going to sound this far away, because that's where the speakers are, and 3 kilohertz is going to sound very close, because there's nothing coming off the side ones. By comparison, BeoLab 90 in narrow mode is a much more constant directivity. So things sound where they are. They sound, a single source will sound like it's in the same place as itself. If we compare to BeoLab 5, as Tua said, BeoLab 5 was made 12 years ago. And one of the goals there was constant directivity. What we wanted, or what they wanted, it's before my time, what they wanted was the same directivity, the same beam width at all frequencies. And you can see they did a very good job of that. That was done by changing the shape of the loudspeaker. What we're doing here is doing it actively, but you can see we have roughly the same width of beam, but now we're more controlled. It's more the same at all frequencies. Yes, it tails in at the top a little bit, but that's the advantage of having the lens on the top of the BeoLab 5. The disadvantage is that you can't change it. So far, so good? Good. Because we have all of those drivers, and up until now, all we're doing is using them to change the width of the beam. We could also change how they behave. So instead of saying we have our main drivers out the front, and we'll use the drivers pointing this way, you saw those on the back samples back there, we'll use those to change the beam width. Instead, we can change the signal processing, the brain inside the speaker, and say, that's our main side. So we use this tweeter going that way, or the tweeter going that way, and say, that's our principal beam. So if you're sitting at the sofa over here, you can say, well, I want the sound to come out the side of the speaker and the side of that speaker instead. So it's like a lighthouse. It's not continuous. We can choose one of 5 different beam directions, but you can then steer the beam that way and sit over there. You're not outside the beam because you've moved in the room. And again, this is because we're using all of those drivers actively. Each has its own amplifier, each has its own signal processing path. So all we do is change the filters. And the end result is that the beam is now facing this way instead of that way. And we call that beam direction control. Finally, we have a new system called active room compensation. For those of you that know the BeoLab 5, you know that we have A, B, C. This is a system where the microphone comes out, it measures how the room changes the sound of the speaker, and then the speaker changes its filtering, its behavior, to offset what the room does. If I oversimplify a bit, what that means is if the room is very boomy, you have a lot of bass in the room, then the speaker takes bass out of its own signal. Because less bass coming out of the speaker plus more bass from the room equals what you should get. It's more surgical than that, but that's the basic idea. With BeoLab 5, what it's doing is measuring the entire room, and it makes the entire room better for everybody. But there's a price for that. If everybody on average is better as they move around, it could be that the unlucky person in the sweet spot, back there, gets worse. There could be a place in the room that is worse because everybody else is better. It's like voting in an election. Not everybody is happy at the end. On average, the entire country is happy, but one person might be more unhappy. Let's look at what we're talking about here. If I take a signal, this signal, send it to a loudspeaker, and then turn it off. In theory, what happens is I get that signal, and then nothing. In reality, what happens is the room keeps singing for me. It's like a bell. If I do that in the room, you can hear the room continuing to ring. So what's happening here is I send sound to the speaker, and the room adds something to the speaker, and then it keeps going by itself. If I subtracted what I wanted from that, what I'm left with is this. This is what the room does. This is an oversimplified case, but this is the room singing along with the loudspeaker. And this is what I don't want. I don't want the room infecting the sound of the speaker. But if I'm clever, what I could do is take that signal and literally flip it upside down like this. So those two are the same, just one is the upside down version of the other. If I then take that signal that I flipped upside down and play it along with what's coming at the listening position from the room, it'll look like this. The red is what I have from the speaker plus the room. The black is an extra signal that I want to send to the speaker in addition to what I'm really sending. And those two cancel each other out. One tries to go up while the other tries to go down, and the end result is nothing. So what I'm doing is sending the signal that I want to the speaker plus the signal that I don't want from the room upside down. And the end result is the addition of these two is this, which is what I wanted in the first place. So what we're doing here is measuring what the room does, finding that out, and then delivering to the speaker the anti-room, you could say. It's the room but upside down to cancel what the room does. But there's a question left. As I said before, with BeoLab 5 and with many room compensation algorithms, they correct the whole room. But this doesn't make sense if you're that person with one chair and no friends. Why, if I have a problem with the acoustics here, should I correct that in the speakers if I only sit here? If I correct for this location, I'll only make it worse here. And I never go there. That's the kitchen. Actually, I always go there, but it doesn't make sense to correct it if I'm only sitting on the couch. So, with BeoLab 90, what you can do is decide. You can take a microphone, and you can do measurements here, and say, this is my sweet spot, room correction, room compensation. I'll do another set of measurements and correct for the area around the sofas. I'll do another set of measurements and correct for the area around the dining room, and I'll do another set of measurements for the whole space. Either that or your installer will do those measurements for you. So now you have different zones that you can select from, the sweet spot, the sofas, the dining area, and the room. And those show up in the app. You can select which one you're going to use. So you can say, I'm sitting in the sweet spot, so I'd like to use that room compensation, please. Or, we're going and having dinner, so let's correct for the dining table. Or, you could say, we're having a party and we're going to move from here to there, so I can do both. And that's a third compensation filter. So what happens is that you do these measurements and build your zones in advance, and then later you can in the app decide which of those zones you're going to use. And you don't have to select one at a time, you can add them together and select multiple ones simultaneously, which builds a new filter for those zones. Okay? In addition to that, active room compensation is multi-channel. Most, if not all, room compensation algorithms look at how this speaker behaves in this room in isolation. And then you measure that speaker in the room, and you fix that one. And they don't know about each other, which is not the way real life works. In the BeoLab 90, the speakers know about each other. So when I send a signal from this speaker, that extra signal that we use to hold on to the room, to correct the room, comes out of this speaker and that speaker. So if you are playing early Beatles recordings where you have John, Paul, George, and Ringo, what you get in this speaker is John and Paul, with a little bit of room correction for John and Paul over there. And George and Ringo with George and Ringo corrected over here. In addition to that, both speakers see what the other is doing to the room. So they know about each other's effect on the room. So in essence, this speaker sees that speaker as part of the room. It's not just this inanimate object over there. It has an effect on the acoustics of the room, and they know that, and they correct for each other. Those were the big three, but there are a lot of other parameters in BeoLab 90 that you can control with that app. Of course, we don't expect our customers to sit with an app and play with parameters all day. That's not what normal people do. That's what geeks like me do. And I love it, but it's not normal. It's very abnormal. So, what you can do is set up all of those parameters, or the installer can set them up for you, and save everything as a preset. So you can have a preset, for example, called movie, or sweet spot listening, or Jeff, because I'm home alone. And you can then recall those. You can go into the app and say, Jeff, and now it's fixed. You can put movie on. You can set up, I think it's 20 parameters, 20 presets, and each one changes almost all of the parameters automatically inside the speaker. That doesn't necessarily have to be done in the app. You can do it in the app. You can have your list of presets there, and you can select which one you want to play with. But you can also select them automatically by the television. The television communicates with the TV using its PowerLink data communication. So what happens is when the TV sees that you're watching a movie, it automatically switches to the movie preset that you've built and set up in the loudspeakers. So that will happen automatically. You don't need to go to the app and switch. The TV will automatically look after that for you. In addition to that, the BeoLab 90 has got a lot of inputs. It's got, for Bang & Olufsen products, a PowerLink input and a wireless PowerLink input. It also has RCA, XLR line in. It has SPDIF, Toslink, and it has USB audio. So that's 7 different inputs, much like a good stereo preamp or a surround processor. What you can do then is say, I want to automate the presets by input. So for example, if you have a high-res audio player connected to the USB audio input of BeoLab 90, when you press play on that product, it automatically switches to the preset that you've assigned to that player. So you don't need to go to the app, you just have to press play on the player and it will automatically switch to the preset that you've set up for that. And that's true for any input. It will switch to the preset that you've assigned to that input. That's the end of my show, and what we'll do in the listening room if you like, or tonight if you like, is go through the other features that are also in there. I've gone through the top 3. These are the big hit list. But there are a lot of other features underneath the hood that are also available. If you want to go through those, stop me. I'll turn into a real geek, and we can go through those. In addition, I think as of today on the website, there's the technical sound guide is available, and that will describe all of the features. The thing to remember when you look at that technical sound guide is that it illustrates something that's really important about this speaker. This isn't just a speaker. If we compare what this is to what you would have to buy to get the same thing from another company, from a competitor, yes, you would have to buy a good pair of passive loudspeakers, but you would also have to buy a couple of very good amplifiers, maybe a couple of monoblock amplifiers, and you would also have to buy a really good stereo preamp and room compensation. And so the thing to remember, and we can talk about this later, is given all those inputs, given the DSP process, is far more than just a pair of speakers. It's far more than just a pair of passive loudspeakers. And we can